Еще раз приветствую всех, кто сегодня...
Once again, welcome back, everyone here in the audience, everyone watching the webcast. This is day 3, the last day of AIJ 2024 conference. And today we talk all things science and research. I'm happy to welcome on the stage one of the most frequently cited researchers, the author of almost 500 research articles, the founder and editor of international scientific publications. Please welcome Professor Swagatam Das. Professor of the Indian Statistics University, Swagatam Das. Scientific approach, the building of an interpretable, fair and transparent AI for the future.
Very good morning to one and all. And I represent the Indian Statistical Institute, an institute which pioneered the study of artificial intelligence more than 6 decades back, besides pioneering the study of statistics in entire Asia. And in next 30 minutes or so, I'm going to share with you some of my fascinating experiences on working on and with the new generation artificial intelligence systems based on foundation models, vision language models, and their fairness and bias aspects in context to medical AI. And if you take a look at this beginning slide, back in 60, 70 years back from now, artificial intelligence started to pour into machine learning. And it was basically one particular machine learning model trained for one particular task, and then it forgets everything. You start training another model from scratch for another task, and this went on. For every different data set, for every medical situation or every situation in banking and finance, fraud detection, you will train a model from scratch, and then the model forgets everything once the task is over. Therefrom, we gradually transgressed into transfer learning, where the model doesn't really forget. It gets trained on a particular type of data, and it remembers the knowledge of that training, and later on it can adapt and extrapolate that knowledge to a new situation. So a machine learning model which learns to differentiate between small cars and big trucks can also differentiate between big cargo vans and big aeroplanes. They can understand these are big vehicles somehow by extrapolating their knowledge. Therein came the transfer learning, which became very popular since 1990s or so. And now we have transgressed towards foundation models. These are extremely big, huge parametric machine learning models, usually neural networks, that are trained on massive amount of external data, and they can perform versatile functionalities. So if you have been using any large language model like ChatGPT or some specific model for Russia, you should know that these models are basically built on foundation models trained on massive amount of external data, internet-based text repositories, and then with simple human prompting. Prompting means programming in your own speakable language. So you give the machine some instruction in your own speakable language, and the machine can perform all those fine-tuned jobs with little or even no examples, in which case we call it zero-shot situation. So we are transgressing from task-specific machine learning models towards foundation models in last just maybe, may I say, 5-6 years or so. And for example, this is the most popular foundation model in computational vision, computer vision application, just published in 2023. We call it SAM, Segment Anything Model. And here what you see is you input a picture and you can segment out any object from the picture. You can ask visual questions on that object. For example, you can segment the cat with black ears by simply with a text prompt that just mark me the cat with black ears, or just by specifying an approximate parametric bounding box around it. Now we are in the era of vision language models, and the interface with users is ChatGPT version 4. GPT-4 is a commercial vision language model which can actually align and fuse both visual and textual representation. So LLM doesn't apply to languages only anymore. They are now meant to process images and give answers towards that from those images, make changes in those images as per user specification. So you see, in this particular situation, when you upload an image and ask, is one cat behind the other? The machine answers, yes, one cat is really behind the other. And then you can segment out that cat by specifying segment the striped cat. Zero shot means you give no example, you specify nothing about the striped cat. One shot means you give at least one example. And the vision language model, which by jargon, a foundation model, can do all these versatile tasks with little or no explicit instruction from the user. So since, I know Russia is the land of great mathematicians, so just this AI foundation model was published very recently in the Nature journal. We call it the alpha geometry model. And it scored 25 on average, which is very close to the score of a gold medalist 25.9 for International Math Olympiad problem. It can solve geometry problems by using abstract constructions, as you can see. It is proving some sort of congruency or equality of angles given the equality of sides for an isosceles triangle so nicely. Now, with great power comes also huge and great responsibility. Need of the hour, when we are trying to adapt such vision language models or foundation models for several tasks around us in healthcare sector, in financial sector, in weather analytics, in astronomy, where not, in computational physics, chemistry. The need of the hour is, of course, responsible AI, which has three most important facets. The first one is fairness. So fairness means the AI algorithms and their outcomes must not favor some specific group or community unduly. And it should give us equitable outcomes across all possible demographies, genders, religions, race, etc., which may be reflected in its training data. Then we have interpretability. Interpretability means every user of the AI system should understand about the internal structure and workflow of the model. If it is a huge, deep neural network, which comes to us like a black box, then this is a limitation on the interpretability of such networks. Okay? So how the model processes any input to its output, what is the workflow? If that is understandable, we call it an interpretable AI model. And the final one is, of course, explainability. The most important facet, when you are using an AI system for your own business or company or academic purpose, for a particular input, why the AI system is inferring something, giving you some decision, that must be understood. The AI system must be able to express that. So here, there is a black box model which, tries to find out some sort of anomaly in the lung X-ray image. And it says the patient has a likelihood of developing pneumonia. But if it is an explainable AI system, it should point out the exact portion of the lungs X-ray image, the fibrosis or the white cloudish pattern, to say why it thinks the patient will have pneumonia. So these three facets, if they are available in your AI system, if they are very much evident during the audit of your algorithm, then everyone will accept it and they will say, you are doing responsible artificial intelligence. However, there is always a trade-off in the world of science. That trade-off classically could be between, speed versus, accuracy, or bandwidth versus time, and so on. Here also, the fundamental trade-off is the more complicated your model becomes, its prediction accuracy enhances, and its explainability goes down, down, down. That's why deep neural networks, they became hugely popular since 2012. But the greatest criticism for them, especially in the academic community, was they are black box. No one understands how they function. On the other hand, decision trees, which are basically a computer data structure representation of a set of if-else rules, are very much explainable. If the features, obey certain rules, then the outcome is this or that. It's extremely transparent. But its applicability in the real world is very low because its accuracy is it doesn't come into any comparison for deep neural networks. So there are certain ways of navigating this problem. One is, can we have a deep neural network, fit it to map an input into an output, and then, just like the concept of an equivalent resistance, can we use a decision tree also to map the same inputs to the same outputs? Then by looking at this explainable decision tree, we know how the deep neural network emphasizes certain features or characteristics of the input objects and infers something. This is one way of making a black box model explainable. Then interpretable models like support vector machines, AOG, HBNs, and of course random forests and so on, their accuracy is also not that high, but they have been playing a very good role in causal inference. And finally, model induction means we can always train a model between the same input-output mapping scenarios to explain a black box model. If we add these three techniques, then the explainability of all these models can improve. Now, coming to my use case, the medical AI. Artificial intelligence is being used for diagnosis and medical report generation and explaining the outcomes of an automatic diagnostic system back to the clinician, staging of different types of tumors and cancers for a long time. Explainability plays a very important role in medical AI. It can bridge the gap between the medical experts or clinicians and the outcomes from an AI system. And on the other hand, fairness is a mandatory feature for any medical AI system. It should not give disparate outcomes based on gender or demography or skin color, etc., etc., etc. So that's why all medical AI systems in India, and I'm sure in other countries, go through algorithmic audit where they check the training data, they check the outcome, and they check how much imbalance is there, how much disparity is there in prescribing certain things for certain genders or race, etc. So the traditional approaches to explainability during the pre-LLM era was like this. This is a very common thing. We call it LIME, or local interpretable model agnostic explanations. You give an image to any machine learning system, and the machine learning system says it's a frog with 54% probability. Now you segment out certain small portions of the image, and you plug in those parts into the same deep learning system and see how many times, with which probability, it's being predicted as frog. If you look at these three segments, you will see that the top one, which segments out the mouth and eyes part of the frog, for that portion, highest probability in the frog class is coming. So we can fit these different predictions from the system through a locally weighted regression, and then the regression pick will tell us, okay, this picture is classified as frog because of this portion, this mouth and the eye part. Okay, that is an explanation. Explanation means why the machine learning system thinks it's a frog. And this is a model agnostic. That means it doesn't depend whether you are using a support vector machine or you are using a deep neural network or you are using a naive Bayesian and so on. Then there comes convolutional neural networks for image classification. And in that case, we use during the pre-LLM era. Pre-LLM era means up to 2022, obviously, because in 2022 November, with OpenAI's publishing of ChatGPT, LLM became very familiar to the broader world. And for pre-LLM era, or for specific applications of medical AI, gradient-weighted CAM, or class activation maps, is very important, which actually highlights the regions of the image where, because of those 4 pixels, the gradient change is maximum. So those pixels are most emphasized during the training process of the neural network. So if you look at this picture, and if the neural network has to find out the cat, it will actually do so. In the second picture, the cat is found out based on those portions that are highlighted, and the dog is found out in the third picture based on those portions highlighted. This is one of our work just in this year in specific medical diagnostics of Alzheimer's patients, and we used 3 different modalities: the MRI images, the genetic data, and the electronic health records. And now we are showing, once the 3 classes, cognitively normal, mild cognitive impairment, and Alzheimer's disease, these are the 3 classes to which every patient should be mapped. Once we get those classes, the right side heat maps are basically showing which portion of the brain of the MRI scan is prompting the neural network to put the image into one of these classes. Sorry. So, with LLM coming into picture, traditional methods got lot of transformed. Okay? Now we have the capability of multimodal explanations, dynamic fairness assessment, and generation of medical reports which could bridge the outcome of the automatic diagnostic system towards patients, and also which could bridge the outcome with the clinicians through explainable interface. Fairness also evolved. LLMs could be used for continuous monitoring and contextual fairness evaluation across multiple demographic intersections. And you know, inside your data, if the domain changes, if there is a shift in the probability distribution of the data, that could also be captured through the fairness evolution. And recent VLMs, vision language models in the medical domain, include, for example, MedPalm2, which is not publicly released, not open source from Google. You upload any such picture of a chest X-ray image or something, and it finds out, it writes down the findings of like a pathological lab expert. On the other hand, MedFlamingo, which is more open source, you upload the picture of your lungs X-ray image, and it can tell you what is wrong with the lungs. It will say, okay, blunt trauma to the left lung with hemothorax. So some sort of blood is being accumulated over there. So these are some most recent VLMs in the domain of medical AI. And what we are trying to do is, with LLM, is that we are trying to make the medical reports simplified, more understandable by common people like us. I don't know about Russia, but in India also the doctors sometimes write down the reports in a very cryptic medical jargon language, which people from my family may not be able to understand clearly. So what we are doing is, through a chained prompting technique, we are using the Llama model for, updating the medical reports. So if you look at the right-hand texts in red and in green, you'll see that, okay, the original medical report says both lungs are clear and expanded, heart and mediastinal normal. So, and the simplified version says both of your lungs look clear and are expanded to their full size, your heart and space around it appear normal. And if you look on the top one, it is more involved: no focal airspace disease, pleural effusion or pneumothorax, cardiomediastinal silhouette is within normal limits. So these are medical jargons, not understandable by common man. And when our system simplifies it, it reads something like, there are no areas of solid lung tissue, no fluid in the lungs, no collapsed lung. The size and shape of the heart and the surrounding area appear normal. There is no free air beneath the diaphragm, which is more, clearer and ready to interpret by a common human being. So bias and fairness in modern AI, I will talk about a little bit of this before I can wrap up. So bias always refers to systematic error in the performance of the model because of giving undue weightage to particular, it could be particular gender, race, religion, some particular group, okay, in the training data. And bias means discrimination. There are several stages in which bias can crawl into your AI pipeline. Bias can come from society to the internet-based data, and the LLMs and VLMs are trained on this huge internet-based data. So the knowledge, the wisdom they acquire from the internet-based data in an unsupervised manner will also be infected with bias. And then there could be such bias in the design of the algorithm. The human beings who are auditing those algorithms or reviewing, they can also be biased. And the main reason is because the gatekeeping is done by those who are in power. That's, of course, the case. So you see, this is a dialogue with ChatGPT. I'm not asking you to read it fully, but it cannot distinguish between gender-neutral language. It associates any gender-neutral term, like professor, with a male gender. If you read it, it always says, okay, she must be the student and he must be associated with the professor. Okay? And the academically higher grade, the professor cannot be wrong, the professor cannot be late, and so on. Must be hardworking. ChatGPT can also create racist and sexist program. If you ask for the JSON description of a person who would like to become a good, scientist, it writes a nice program, but the program says if the race is white and the gender is male, then the person will become a good scientist. So this is the spontaneous answer from ChatGPT, and you can see the bias present over here. Google image search, which uses a neural network-based image fetcher, is hugely biased. If you search for CEO, after 11 male rows, it shows all leading CEOs, including Steve Jobs and Mark Zuckerberg and so on. And the 11th row, you can see the only lady CEO, which is a Barbie doll. So this is the result from Google image search, extremely biased towards male and towards academically or industrially hierarchies towards the male. So what is fairness? Fairness in machine learning refers to the ability of the algorithm to provide you equitable outcomes and unbiased representations. For example, if you look at this picture, if you just make it bipartite, this side is for a white-skinned Western bride, and that side is for a typical Indian bride with a darker skin. The machine learning algorithm can tell you that, okay, the left side picture belongs to a bride, but the right side picture doesn't belong to a bride, although both are brides, because of the skin tone difference. So these are very famous examples, the Compass software results, which was used for law enforcement in some provinces of USA, and it associated much greater risk with the dark-skinned people because of their skin tone, although their past criminal records were much less severe than the corresponding white-skinned, criminals. Similarly, a study by Timnit Gebru, Deborah, Raji, and Joy, their group showed how the Amazon software for face recognition is extremely biased and gets to much more error in recognizing female faces than male faces, in recognizing dark-skinned faces than white-skinned faces, and so on. So lack of data diversity and represent gaps. The entire machine learning paradigm, the deep learning systems that are nowadays within industry applications, including ResNet, LLMs, and so on, they are trained on, most of them are trained on the ImageNet dataset, which contains 14 million labeled images. Out of the 14 million labeled images, okay, you can see how disparate is the proportion of images from other countries, only 37.8, United States of America 45.4, and Canada, Italy, all these are white-skinned images from developed countries. But how many people from other distribution of the population in the world can contribute to ImageNet? As a result, because of this disparate distribution, the machine learning system trained on ImageNet also gives you similar outcomes. They're biased, which must be corrected. How can we quantize fairness in AI? There are a lot of indices. I will introduce some of them here before I wrap up. For example, the demographic parity or statistical parity, which says if you have two sensitive groups, then the proportion of their assigning to a particular category should be same in both the groups. And the difference of these two probabilities gives you the DPD, or demographic parity difference. Suppose these are loan applicants, and we have both genders, male and female. If you look at the male applicants for whom the loan has been approved, it's 3/4 of their total, 3/4 fraction of their total population, which is 0.75. For the female applicants, the proportion of loan approval is only 2 out of 4. There are total 8 candidates here, and you can see it's only 0.5. So we say the demographic parity is not satisfied if the proportion of loan approval is not equal for males and females. So it's not satisfied. And it says that, okay, the loan approval system is unfair because the approval rate is higher for males than for females. This indicates a potential bias in the system, and the model doesn't meet the fairness requirements. Whenever you are, you are marketing industrial software based on AI, the auditing team will look for whether the fairness obeys these quantitative metrics. Similarly, we have equal opportunity in medical AI, which ensures true positive rate across groups, similar true positive rates, equality of true positive rates across group. And so, for example, equal likelihood of correct diagnosis of different ethnic groups, calibration, which ensures predicted probabilities match actual outcomes across the group, conditional use accuracy equality, treatment equality, and of course, favorable treatment equality, which are all trying to see how equal treatment facilities have been provided across different demographies or different classes that are inside your training data or inside your use case. And in medical AI, we can always fit a fairness-aware loss function. For example, when you train the particular medical deep learning system, your original cost function could be the L task, and which is regularized by the difference between the true positive rate between two communities. For one, A equal to 0, maybe the dark skin people, and for other A equal to 1, maybe for the light skin people. You try to also minimize the square of this difference. Or maybe for male and female, you try to minimize the square of this difference. So defining fairness and bias in healthcare data, we can quantify them using several factors, including inclusivity, diversity, and labels. Metrics may include representation across gender, skin tone, ethnic group, and age. So a person from USA, given the same age and maybe much healthier or obese, and a person from India, same age, not that obese, you cannot prescribe similar medicines for treating their diabetes. Okay. Similarly, the most important part comes when it is about skin lesion detection. So one last use case for us, this is one problem that we are trying to solve, skin tone bias and class imbalance for skin lesion classification. Deep learning models, when they come to melanoma, melanoma is a type of skin cancer which is very common among the dark-skinned people. But there are data sets for training such medical deep learning systems which are extremely biased towards the white-skinned people, and they cannot easily detect the melanoma skin patches or lesions on the dark-skinned people. If you look at these two are the representative data sets, ISIC-18 and ASAN. Both the data sets, a network trained on ISIC-18 may struggle with darker skin tones, while the one trained on ASAN could also fail on light skin tones. And for training deep neural networks on skin segmentation or lesion detection, these two are our only options. They are very well documented, they satisfy all the medical parameters. So, can we really overcome these challenges with limited data sets? The answer is yes. We have to augment them, we have to mix their patterns, we have to make a smooth transition. Only then it is possible. So to meet up these questions, recently this year we published one very nice paper in the MICAI conference. MICAI is the most acclaimed conference in medical imaging. And we gave a solution where we are using data augmentation through adaptive mix-up sampling and also cross-sampling across diverse skin tones. Basically, we are mixing the lighter and darker skin tones to make a smooth transition and creating new images to make our classifier much less biased towards the, the darker skin patches. This work and all its codes, etc., are available from the website of MICAI, and it may mark a significant step because we can actually artificially populate the data sets. So, 4 emerging issues that the modern AI powered by LLMs and VLMs must overcome: bias, lack of explainability, ethnical concerns, and misinformation. We have miles to go before we can flip. Explainability is very important. It is an essential condition for marketing any such AI system. Bias and fairness, we have to be very careful about them. Continuous monitoring is essential because the demography and the distribution of the training data can change. Nowadays, all AI systems operate through lifelong learning, so they can update themselves through continuously getting new use cases, new patients, new training data. And for those new things also, the bias and fairness must be mitigated. And finally, adoption through explainability, clear, understandable explanations of AI decisions increase the adoption for healthcare professionals, in fact, for all professionals who are using AI. So with this, I would like to thank you very much for your kind attention. This is a picture of Professor Prashanto Chandra Mahalanobish, who was the founding father of my institute, Indian Statistical Institute, who is welcoming Professor A.N. Kolmogorov, another giant statistician from Soviet Russia, long back in April 1962. So, thank you very much for your kind attention.
Professor Swagatam Das, please applause to the speaker. Thank you very much. You are welcome here in Russia. Thank you. Аплодисменты, Swagatam Das.
A round of applause, please. The professor of Indian Statistical Institute, Swagatam Das, was talking about the scientific approach to building a transparent and fair and unbiased AI for the future.